For our final example of objective 2, which is all about where a function could be differentiable, where derivatives fail to exist, find the values of a and b so that f of x is differentiable everywhere. And we have ourselves a piecewise function. So for this particular piecewise function, we've got, let's say we got a parabola up here. We've got this a and b that we're trying to figure out what they are. Well, a parabola, a quadratic equation, is going to be differentiable everywhere. There's no sharp turns. There's no vertical tangent line. There's no discontinuities. And the same thing is true for this linear function that's down at the bottom, which means that the only place where it could possibly not be differentiable is right here at 1, where the two pieces join up. Well, do they even join up? That's a good question. As a matter of fact, that's the first thing that we have to contemplate. Do these things join up? That's called continuity. So we're going to check the continuity. Before we even do a derivative, we need to make sure that the function's continuous. Basically, that the line and the parabola, the y values, match up right here at 1. Because here's what it could look like. For example, we have a parabola on the left side of 1, and then we have a linear portion on the right side of 1. If there's this big gap in between here, it's not continuous. If it's not continuous, the derivative is not going to exist. So we need to first force these two y values to be the same. Look, I did it again. Come on. All right, well, that graph is going to disappear. We're just going to have to deal with it. So continuity, we're going to switch back to just regular limits. We're not taking a limit of a difference quotient. We're just taking the limit. So the limit as x approaches, we want to do 1 because that's the breaking point. And we're going to do it from the left-hand side and the right-hand side of 1. So the limit from the left at 1 of f of x. Since this is a piecewise function, from the left at 1, that means numbers that are smaller than 1. That's the top branch up here. So I'm going to use the parabola for that part. The limit as x approaches 1 from the left of ax squared plus b. Well, ax squared plus b is quadratic. Quadratic's polynomial. Polynomials are continuous everywhere. If they're continuous everywhere, then that means the value of the limit here is the same thing as the value of the function. You just plug it in. That's just what it means. It just means you plug in 1. 1 squared is 1. I'm going to have a plus b. All right. What about from the right-hand side? The limit as x approaches 1 from the right of f of x. This means numbers that are bigger than 1. And for our function, numbers that are bigger than 1 are going to use this bottom branch here, which is the linear one. For x minus 1? Yep. Okay, so yeah, it's continuous everywhere. Therefore, the value of the limit and the value of the function is the same. We can just plug it in. 4 times 1, 3. 4 minus 1, 3. Yeah, there's our 3. Okay, in order for this function to be continuous, the limit from the left and the limit from the right have to be the same. And that means that a plus b, whatever they turn out to be, have to add up to 3. Well, how many different things add up to 3? A whole bunch. Like, for example, maybe we choose something like 1 plus 2 equals 3. Wow. This is right. This is math that you do in calculus for sure. So 1 plus 2 definitely equals 3. So what if I chose those numbers? If I chose those numbers, then I'd have 1 times x squared plus 2 for that top branch. Just x squared plus 2. Let's see what happens. I'm going to go over here to Desmos, and I'm going to graph these two things. This line's getting on my nerves, so I'm going to get rid of it. I'm going to see what happens. So come over here to Desmos. And in order to do different pieces, you just have to multiply it by its condition, like its domain. So the top branch here is going to be y is equal to, we said x squared plus 2, and then in curly brackets, I'm going to type in its condition, which was less than 1. So x is less than 1. All right, there's that branch. And then I'll hit enter and I'll put the next branch in there as that linear function, y equals 4x minus 1. And I'm going to also multiply it by its condition, x is greater than or equal to 1. There we go. And then there's that branch. Okay, so you can see that it's continuous there, but if I try to zoom in right there at 1, you can see that there is a sharp turn, kind of a cusp that's right there. So no matter how much I zoom in, and zoom in, and zoom in, it never flattens out completely, which implies that the derivative would not exist there. It's not locally linear at that particular point. So we've only done half the job. The a value can't be 1 and the b value equal to 2. So how do I figure out what they have to be so that it does join up to be nice and super smooth there? So let's see. Let's go back over here. And this time, we're going to do some continuity business. No, we've already done continuity. Differentiability business. Did I spell that right? We're going to go with it. So here, we're going to take the derivative from the left at, the derivative from the left at 1. And I'm going to write that one-sided limit for a difference quotient. The limit as x approaches 1 from the left, and then we'll do our difference quotient, f of x minus f of 1 over x minus 1. All right, now let's plug our stuff in from the function. And since we're talking about the left side of 1, once again, that should just be this top branch here, which is this ax squared plus b branch. Limit as x approaches 1 from the left. Our f of x is ax squared plus b minus our 1. Well, if I plug in a 1 in here, I'm just going to get a plus b if I plug in a 1 there. So maybe in parentheses, a plus b over x minus 1. And then let's do some simplification. I'm going to get rid of these parentheses. Yeah, that's the right word. Distribute the negative sign. And when I do, how convenient is this? The b's cancel. Okay. And then rewrite, simplify, and stuff. Limit x goes to 1 from the left. Ax squared minus a over x minus 1. Well, what happens when we stick in 1? 0 on the bottom, of course. And then this would be 1. I'd have a minus a, which is also 0. 0 over 0. I've got to fix it. I've got some sort of hole. Well, I can fix this polynomial, which means probably common factor I've got to cancel out. Limit as x goes to 1 from the left. Notice they have a common factor of a, so I can pull that out. GCF a, x squared minus 1 over x minus 1. Still not done, because I've got a difference of 2 squares up here. I'm going to have a times x minus 1 times a x plus 1 over x minus 1. And there we go. Here's our hole that we're about to cancel out. Boom, boom. And then finally, my gosh, this has been forever. From the left, I just have a times x plus 1. All right, whenever I plug in 1, 1 plus 1 gives me 2. I have 2a. So we just discovered that the derivative of this parabola part from the left at 1 needs to be 2 times a. Let's do the same kind of thing from the right-hand side. And you know what? We're going to shortcut that one just a little bit. F prime from the right at 1, that should be equal to the limit as x approaches 1, this time from the right, of f of x. Well, it's a line. I'm not going to go through and do the whole entire limit definition of the derivative. What's the slope anywhere on this branch? It's a line, so the slope's got to be 4. So no matter what, this thing has got to be equal to 4. If you do this same exact limit definition kind of thing for that line, we've already showed that in another video. It was super fun. You're still going to get 4, the slope value for that particular line. Okay, so now then, if the derivative is going to exist at that particular point, then that means that these two values need to be the same, that 2a has got to be equal to 4. In other words, a has got to be equal to 2. If a is equal to 2, then it's going to be differentiable everywhere. at that particular point, but everywhere because on the left side's a parabola and on the right side's a line. So let's go back up here to this one. What we just discovered is that A has to be 2, which means B actually has to be 1. So, oh man, I almost guessed it. It's 2 plus 1, not 1 plus 2. Should be 3. So now let's go back up here to this function. Clean this thing up. It's looking like rubbish. And make this 2x squared plus 1. And I'll go back to Desmos. I'm going to fix this function, and let's see what happens. So I need to come back up here, put a 2, and then over here, make this thing a 1. Now let's look at our graph. If I zoom in at that particular point, it's impossible to tell that there's a difference between being something that's quadratic on the red part and then that's something that's being linear. It's a nice flat straight line. So just kind of a recap of what we did here. Boom and boom. We first had to make sure it was continuous. I did it with limits, but if this is a multiple choice, all you got to do is set those y values equal to each other. Easy. If it's free response, though, you need to do the, the limit notation, all of that stuff, and be totally thorough. For the differentiability, it's the derivative of the top piece needs to be equal to the derivative of the bottom piece. And we have to, as of right now, do that with limits because we don't know another shortcut way, as if there's a shortcut. Anyway, and then we developed ourselves a system of equations, and solving that system of equations gave us the values of a and b so that that function was continuous and differentiable everywhere.